All right. Good evening, ladies and gentlemen. Welcome back to another live virtual public program presented by the Museum of Flight in Seattle, Washington. Thank you so much for being here with us tonight. My name is Cale Wilcox. I am the Public Engagement Manager down there at the museum, and we are excited to be able to bring you this virtual programming while we still navigate health and safety during this time of the pandemic. I'm really excited for tonight's program. I think you're all going to enjoy it. I know it's a topic that a lot of us are interested in. It seems like these days, every day, there's something new to get excited about in space science and space travel and research. And this topic is absolutely no exception to that. And one that I know for a lot of people has been a long time coming to get updates and get official information about. So tonight, we're going to be taking an in-depth look into the exciting new James Webb Space Telescope. The next generation of deep space imaging will arrive with the launch of the James Webb Space Telescope in late 2021. And I believe our presenter will be able to give us a firm date on when that launch date will be soon coming up here. Our speaker tonight, Héctor Delgado Díaz, will be discussing the fascinating science that can be done with this technology, including how we can use efficiently the James Webb Space Telescope to possibly find life in planets outside of our solar system. Now, at the conclusion of Hector's presentation this evening, we will have some time for audience questions. On YouTube, where you're watching right now, you can type your questions into the comments section there, and we can see them on our end, and we'll be able to get those answered for you at the end of the presentation. Let me tell you a little bit about our speaker tonight. Héctor Delgado Díaz is a third-year PhD astronomy and astrobiology student at the University of Washington. He works with Dr. Victoria Meadows, analyzing how to maximize the amount of information we can obtain from the atmospheres of planets outside the solar system using the new James Webb Space Telescope, in order to determine the possibility of life outside of Earth. Prior to his PhD, he completed his bachelor's degree in the general sciences at the University of Puerto Rico and his master's in physics at California State University, Los Angeles, where he completed his thesis work at NASA's Jet Propulsion Laboratory. When he's not doing his work, he enjoys learning new languages, playing video games, and participating in science communication activities. Help me welcome to the museum tonight, Héctor Delgado Díaz. Hello, Hector. How are you?
Good, and you. Thank you so much for that introduction.
Yeah, absolutely. Thank you for being here with us tonight. Where are you joining us from this evening?
I'm joining from Seattle, so anyway.
Excellent. Well, we always like to have hometown experts talking to our audience. So at this point, Hector, I'll bring your presentation up onto the screen here, and I will turn it over to you, sir, and I'll see you back when it's time for questions and answers.
Sure. Okay. Thank you again. And as Cale said, my name is Héctor Delgado Díaz. I'm a third-year PhD student in the University of Washington in the astronomy department. And I'm going to talk about the James Webb Space Telescope. So for the nth time, and hopefully last time, the launch of JWST is upon us. If you get the joke, hope you liked it. If you didn't, you're going to understand in a bit. I also would like to say first that because this is a virtual talk, I'm not going to use many videos as I would have loved to, because they tend to get frozen and lose quality when screen sharing them. However, I still hope you enjoy the presentation. Also, big thank you to the Space Telescope Science Institute, because they were the one who provided me with resources to provide you to a good presentation tonight. So, who would kidnap a space telescope? A couple of months ago, this was the headline for an article in The Atlantic, where it was mentioned that NASA had fear of a possible pirate attack when transporting JWST from California to French Guiana. This might sound unreasonable at first, but when you think about it, JWST is the most technological space telescope that will be launched. It has cost $10 billion. It has been more than 20 years in the making. So not only it is a high-priced telescope, but it also holds significant value for the scientific community. And if it were to get robbed, let's just say ransom money was not part of the budget proposal for this telescope. So before we go deeper into learning more about JWST, or the James Webb Space Telescope, I want to talk about why we need space telescopes and also a brief history of them. When we're trying to learn about the universe, we use many different telescopes that help us see the sky in different types of light or wavelength. And they're called, the types of light are called radio, infrared, optical, ultraviolet, X-ray, and gamma ray. However, because Earth has an atmosphere that helps us not only to live thanks to oxygen and other nutrients, it also protects us from harmful light like the UV from the sun. This means that not all light can reach the surface of the Earth, including the highest mountains. As you can see, some of the radio, infrared, optical, which is known as visible light, the one we can see, and UV can reach the surface of Earth. But not all the light can not but to study other types of light, we need to be higher up to see the desired light that we want to study. Thus, we need space telescopes to advance the astronomy field. It is also worth noting how different types of light are represented. Some lines look more stretched out than others. This is what we call wavelength, which will be talked throughout the presentation. Now, a very brief journey through time, the history of space telescopes. There has been many satellites and small telescopes that have been launched. However, I will only focus on the great observatories or telescopes that were multi-purpose and long-term use. First up, we have the Hubble telescope. It was launched in 1990 and is still working at this current date. The light that it observed was ultraviolet, visible, and near-infrared. Named after Edwin Hubble, a famous astronomer known for recognizing that there are more galaxies in the universe than just the Milky Way, and also for paving the way of observational cosmology. This telescope was the first one of the great observatories missions led by NASA, which were telescopes designed for this multi-purpose and long-term use. It produced many famous images, like the Pillars of Creation, located at the Eagle Nebula. These are 3 columns of cold gas, where at the tip of each column are regions where stars are being born. Aside from breathtaking images, Hubble made various discoveries in the solar system, such as 4 moons of Pluto, Nix, Styx, Charon, and Kerberos. It discovered other planets around other stars. For example, in the middle of this picture, there's a star called Fomalhaut, and in the instead of the picture, there's Fomalhaut B, a planet orbiting that star. And it even looked very deep in our universe, which has helped us understand the evolution of the universe and the behavior of early galaxies. Here is the famous picture from Hubble Deep Field Image. And while this telescope has done amazing science, it also had some slight problems. For example, there was a spherical aberration on the lens that would produce blurry images and a halo around the object. Also, 4 out of 6 gyroscopes failed, and the telescope went into safe mode, basically shutting down. So NASA had to coordinate what we know as servicing missions. Astronauts were sent to space to repair the telescope in a total of 5 missions that spanned from 1993 to 2009. They were able to solve the issue. And as you can see in these pictures of the Galaxy M100, where on the left, it was taken on November 1993 before the servicing mission 1, and on the right, taken on December 1993 after the mission. And you can see the clarity of the galaxy now. So a fixed Hubble is a happy Hubble. Although this year, Hubble had a computer failure scare, but it was also fixed, thankfully. It is also worth noting that the last servicing mission in 2009 was meant to maintain Hubble so it could run and overlap with JWST, which was supposed to launch in 2007. Hence, Hubble is still working while waiting for the arrival of JWST. The next telescope is the Chandra telescope. It was launched in 1999 and still currently working, and the light it observed was the X-rays. This was named after Subramanian Chandrasekhar, an Indian-American astrophysicist known for his work on stellar evolution and black holes, particularly what we know as the Chandrasekhar limit, which is the upper mass limit for a stable white dwarf. Because this telescope observes in the X-rays, it has given us many important images because ground telescopes can't observe wolfing X-rays due to the atmosphere. Some of its exciting and wonderful scientific discoveries are the young supernova remnants of Cassiopeia A. It helps us study the anatomy of a supernova by looking at the X-ray emissions of the leftover gas. When observers around the world first reported seeing the Crab Nebula in 1054 in the Common Era, they described it as a new star. Chandra gave us a new view into the heart of the nebula that was left behind after a supernova explosion, revealing new details about the area around the central pulsar. Chandra's observation in X-rays have allowed us to trace the movement of the particles in its bright ring for more than 20 years, and also evidence for thousands of black holes located near the center of our galaxy, the Milky Way, as well as many other discoveries related to high-energy physics. The telescope also had issues with the gyroscopes, like Hubble, but this happened about 90 years after its deployment, so failures are expected. However, the issue got solved and the telescope is still running. And finally, we have the Spitzer telescope, launched in 2003, but got decommissioned in 2020, so its last year of work was last year. The light it observed was in the infrared. This telescope was named after Lyman Spitzer Jr., an astronomer that was the first to conceive the idea of a space telescope. He also did research in star formation and plasma physics. Some of the discoveries made possible with the Spitzer telescope were optically invisible infant stars, known as protostars, that appear as pink and red speckles in this image of the snowflake cluster. The detection of an exoplanet system with 7 exoplanets similar to Earth size named TRAPPIST-1. An exoplanet is a planet that orbits another star, and TRAPPIST-1 is the name of the star, and the letters, for example, B, C, D, E, F, G, and H are the names for the planets orbiting those stars. And also big baby galaxies, which are galaxies formed in the early universe, approximately 13.4 billion years ago, and are larger and more mature than what scientists thought they should be. As you can notice, the 3 telescopes observe the universe at different wavelengths, meaning all of them could have looked at the same part of the sky but see something completely different. With many of the discoveries by all of this and many other telescopes, a vast amount of questions were answered. But as it usually happens in research, more information leads to more questions. Therefore, this is where it enters the James Webb Space Telescope, or JWST. To give a brief history of JWST, in 1989, the Space Telescope Science Institute, or STSCI, and NASA co-hosted the Next Generation Space Telescope Workshop, which sparked the idea of a telescope that would probe further into the infrared light and would be the follow-up of Hubble, which was supposed to be decommissioned in 2005. And thankfully, Hubble is still up and running, and it didn't get decommissioned many years ago. This was the first design concept of the telescope, created in 1996, and as you can see, it already includes a segmented mirror. The budget for this mission, $500 million. In 2002, it got renamed to the James Webb Space Telescope. However, it has been lately debated to change the name due to James Webb being knowledgeable of the lavender scare back in mid-20th century, as he was in a leadership position at the Department of State. Yesterday, this news article came up in the New York Times, and it's a good read to understand the current issue. Now, going back to the timeline, the first launching date was set for 2007. However, construction of the telescope and its instruments started in 2002 and did not end until 2016, so the launch didn't happen. So now the estimated budget of the telescope is $825 million. In 2016, the construction of the telescope was completed, finally. However, the estimated budget increased enormously to $8 billion. This is mostly due to many of the delays and the operational costs to maintain and reserve the already built pieces of the telescope. Now, not only the telescope got delayed back in 2007, it got delayed a couple more times. March 2018, June 2018, July 2020, June 2021, September 2021, and lastly, December 18, 2021. This is the date that it's hopefully supposed to launch officially this time. Hence, that's why the name of the title of the presentation. And the estimated budget for the telescope has reached $10 billion. With all of this taxpayer money, clearly there is a lot of expectations for the telescope to do as it should and possibly more. Fun fact, the average income tax paid per taxpayer in 2018 was $15,000, meaning that it would require about the population of Vermont to fund this budget. So what are some of its features and properties that makes it expensive? Where will JWST orbit? Why does it have a hot and a cold side? Why is it an ambitious piece of engineering? Let's explore all these questions, and we're going to talk about all about the telescope now. Several innovative and powerful new technologies make JWST's ambitious science goals possible. Examples include specialized optics to align the mirrors, detectors that can capture and separate light from hundreds of sources at once, and thermal control systems. These technologies make Webb the most sophisticated and complex space science telescope ever created. JWST is a collection of movable parts that have been designed to fold into a compact formation that is considerably smaller than when the observatory is when fully deployed. This allows it to just barely fit in a 16-foot rocket payload frame. So it's about the size of 3 women of average height in USA, which is 5'4". And since Webb's mirrors need to fold to fit, engineers ensure its 18 mirror segments can also be adjusted from a single perfect focus. Each mirror segment has an actuator or a tiny mechanical motor attached to the back, allowing operators to move each one of them separately. JWST's tennis court-sized sun shield is deployed by 139 of these tiny mechanical motors. It has also 8 major motors and thousands of other components, which can fold and stretch the fine membranes of the sun shield into its final touch shape. Now let's look closer at its mirrors. JWST has a 6.6 meter or 22-foot diameter primary mirror. It's quite large, and that's for several reasons. For context, Hubble mirror is much smaller at 2.4 meters or 7.8 feet, a little bit bigger than a tall person size. And this is in diameter. Its mirror also needs to be stable at very cold temperatures, meaning 40 kelvins, which is roughly negative 390 degrees Fahrenheit, which is why it is made of beryllium, which is 6 times stronger than steel and 2/3 the density of aluminum. There are 18 hexagonal segments. They're hexagons, so the mirrors can be adjusted to align without gaps and form a circular shape. Now, each segment is coated in a very thin layer of gold, about 1,000 atoms thick, so it's very thin, this layer. Gold was selected because it is the best reflector of infrared light. So how will JWST conduct its science operations? Let's start with a bit of context. The Whirlpool galaxy, seen here in the background, is about 87,000 light years across and 31 million light years away. For reference, from Earth to Sun, there is a distance of 1 astronomical unit or 93 million miles. In terms of light year, which is the distance light travels in 1 year, there are just 8 light minutes. So meaning that the light from the sun to Earth, it takes only 8 minutes to reach to us because it's traveling at the speed of light. So that means that we need 63,000 times more of this distance to just make 1 light year. Now remember, the Whirlpool galaxy is 87,000 light years across, but it's 31 million light years away. Those are big numbers. And in any case, you can think about it another way. As seen from Earth, the galaxy is about 1/3 of the size of the moon on the sky. So each of JWST's 4 instruments are like a Swiss Army knife of more specialized components with multiple ways of observing. And although some instruments are more suitable than others for observing specific types of targets, all 4 can be used for investigations of the wide variety of objects that make up the universe, including planets, stars, nebulas, and galaxies. So JWST's 4 science instruments are sensitive to a range of infrared light. In here in this picture, you can see the two different main types of light. We have the visible and we have the infrared, which is subdivided into near infrared and mid infrared. The near infrared spectrograph, or NIRSPEC, is one of JWST's versatile tools for near-infrared spectroscopy, which spreads out light into its component wavelengths like a rainbow. This instrument has the first multi-object spectrograph in space, known as a microshutter array. It can capture individual spectra of dozens of objects at once, making it ideal for efficiently studying many distant, faint galaxies and exoplanet atmospheres. Next up is the near-infrared imager and slitless spectrograph, or NIRIS. It will also gather spectra and photograph the universe at near-infrared wavelengths. It can study the composition of exoplanets' atmospheres, observe distant galaxies, and examine bright objects that are very close together. The near-infrared camera, or NIRCam, is JWST primary imager, or JWST's camera. It delivers high-resolution imaging and spectroscopy for a wide variety of investigations. It will detect light from the earliest stars and galaxies in the process of formation, stars in nearby galaxies, young stars in the Milky Way, and objects from a distant region of our solar system called the Kuiper belt. That's where Pluto orbits. It can also track the motion of exoplanets as they orbit their star. The mid-infrared instrument, or MIRI, is another powerhouse. It can take images and gather spectra. It covers larger, longer, and redder infrared wavelengths of light. As the only mid-infrared instrument, astronomers rely on MIRI to study cooler objects like debris disks around stars, which emit most of their light in the mid-infrared, and extremely distant galaxies whose light has been shifted into the mid-infrared over time. I will explain this more later in future slides. So I've mentioned spectrographs and spectra several times. Usually, the spectra of the objects are humbly hanging out behind the scenes of some of the most intriguing headlines in astronomy, and they provide an incredible amount of information. Spectrographs are instruments that spread the light out so that the brightness of individual wavelengths can be measured. The result is known as a spectrum. By looking at the resulting patterns in brightness, we can learn about the composition, surface temperature, density, and movement of objects in space like planets, stars, nebulas, and galaxies. JWST has different types of spectrographs, each designed for a slightly different purpose. Plus, the telescope is the first one to have a multi-object spectrograph in space, which means we can get separate information about many objects, like individual stars, within just one observation. Now, where is JWST's orbit? JWST orbits the Sun near the second Sun-Earth Lagrange point, and this is referred as L2. And here, this is a point where the gravity from the Sun and the Earth balance. This point is approximately 1.5 million kilometers from Earth on the far side of Earth from the Sun. JWST can't orbit the Earth like Hubble because the visible and infrared light from the Sun, Earth, and reflection of the Moon would heat up the telescope mirrors and scientific instruments, causing the telescope itself to glow in infrared light, and that would outshine the faint objects in space. JWST will not be located precisely at L2, at the Lagrangian point 2, but will move in a halo of orbit around L2 as it orbits the Sun. At L2, JWST can maintain a safe distance from the bright light of the Sun, Earth, and Moon, while also maintaining its position relative to Earth. Now, can JWST be serviced over here in case of emergency or repair, like it happened with Hubble? Unfortunately, no. To meet JWST's science goal, the telescope has to be far away from the heat of the Earth. This is why the telescope had to be so thoroughly tested before launch. However, this isn't the first mission that is unserviceable. Other space telescopes, such as Spitzer and Herschel, have successfully completed their mission time in unserviceable orbits. Now here, I will show you a video of how it works and how will the orbit of JWST will seem throughout the course of the Earth orbiting around the Sun. So as you can see here, JWST is a yellow trail and it's orbiting in a circular motion at what is called the Lagrangian point, the second Lagrangian point. It is following Earth, so we'll be always nearby the telescope, and it will not carry out far away from it. And as you can see, the sun shield, which is the part that covers the telescope from the light of the sun, it will always be facing the sun. So the telescope will never face Earth. It will always be on the other side of the motion throughout the orbit of the sun. So now going back to the presentation. So as shown in the video, the lower part of JWST, where its 5-layer sun shield, faces the sun. This is where its ambient temperature equipment, like its solar panel, antenna, computer, gyroscopes, and navigational jets are. It's a tennis court-sized sun shield that protects the telescope from external sources of light and heat, which ensures it can detect faint heat signals from very distant objects. It's very important for its observing site to be very, very cold. JWST's science instruments are housed behind the mirror, separated from the warm communications and control technology by the sun shield. They are around here, as you can see it. Now, JWST needs both passive and active cooling. Its 5-layer sun shield provides passive cooling. The first layer of the sun shield is 0.02 of an inch, so 0.005 centimeters thick, while the other 4 layers are only 1,000 of an inch thick. There is also a cryocooler, essentially a sophisticated refrigerator or air conditioner, to support one of its instruments, which is the MIRI, and this is the active cooling element. Maintaining these temperatures ensures that JWST can gather a greater range of infrared light in space. Without cooling, the only thing that the telescope would see would be itself. Since warm things glow in infrared light, JWST has to be colder, or else its self-emission would produce enough background light that it would overwhelm faint sources. The colder the telescope is, the fainter things it can see, up to a point, because other background sources will be the ones overwhelming the telescope. JWST's glow would still be the greatest background source at mid-infrared wavelengths. In depth, to understand how the cooling system works, the sun-facing layer estimated maximum temperature is 400 kelvins, so around 260 Fahrenheit degrees. So in here, we have the sunlight, and when it hits the sun-facing layer, it would be at 400 kelvins. But once that heat starts going through the other layers of the sun shield, it will start dissipating the energy, and it will lower it to 40 kelvins degree, which is the 40 kelvins, which is the temperature needed for the science instruments to work as they should. However, because MIRI needs a little bit of more of cool, it has the cryocooler, which would then add a little extra cooling to the system. Thus, all the instruments should work perfectly. A couple of months ago, JWST was carefully folded up and loaded onto a ship, which passed through the Panama Canal on its way to French Guiana in South America, where it reached its launch site at the European spaceport located near Kourou. It is beneficial for launch sites to be located near the equator. The spin of the Earth can help give an additional push to the rocket. After launch, the first month in space, on its way to the second Lagrange point, or L2, the telescope will undergo a complex unfolding sequence. Steps include deploying, tensioning, and separating Webb sun shield, a 5-layer diamond-shaped structure, extending the secondary mirror support structure, and unfolding the primary mirror, which has a honeycomb light pattern of the 18 hexagonal gold-coated mirror segments. Deployment and commissioning will take at least 6 months. Engineering and scientists will carefully activate and confirm each and every instrument is working properly before the first image of a star field is delivered about 2 months after it launches. It's worth noting that this first image would be completely unfocused, so it wouldn't be a useful image. It's just to confirm that they are working. On the 3rd month after the launch, JWST will complete its first orbit around the Lagrangian point 2, so it will complete the donut orbit that it was doing, and take the first focused science quality image. After the 6 months mark, it will begin its science mission and start to conduct routine science operations. So after 6 months of after the launch, that's when the science will really happen with JWST. Now, how do we talk to JWST? So every great relationship is based on excellent communication, right? Well, the Space Telescope Science Institute, the STSCI, located in Baltimore, Maryland, plays a key role in communicating with it. It hosts the telescope's Mission Operations Center, where engineers and scientists command and control the telescope. This will be here in Maryland. And then commands from STSCI will travel to the Deep Space Network antenna located in Goldston, California, which then will transmit information to the telescope. Then the data that the telescope gathers, it will be returned through the DSN, the Deep Space Network, and then back to the STSCI, where the data will be processed, distributed to the scientific community, and later archived. JWST has been an international collaboration since the beginning. In addition to the United States, 13 countries are involved in building the telescope: Austria, Belgium, Canada, Denmark, France, Germany, Ireland, Italy, the Netherlands, Spain, Sweden, Switzerland, and the United Kingdom. Additional member states in Europe also contributed to the European Space Agency, the ESA. NASA is the lead partner on the project, working in conjunction with ESA and the Canadian Space Agency. The Space Telescope Science Institute conducts the science and mission operations from Baltimore headquarters. As the lead agency, NASA has overall responsibility for JWST's mission. More than 120 American, European, and Canadian universities, organizations, and companies in 14 different countries and over 29 US states contributed to JWST. Now on to my little bias, the best part of the presentation. Let's explore the universe with JWST. What was the universe like after the Big Bang? What are the characteristics of galaxies as the universe aged over billions of years? What more will we learn about how stars form, live, and die? Since JWST can see through dust, what will it reveal about forming planets and other distant worlds? These are only a few of the questions JWST will help answer. The telescope will contribute to all areas of astronomy, and its most exciting discoveries may be the ones that we didn't anticipate. The science that will be done using the telescope will bring us closer to NASA's overarching science goals of discovering secrets of the universe and searching for life beyond Earth. As NASA's most ambitious and complex astronomical space observatory ever, the JWST will deliver amazing science, complementing the spectacular scientific discoveries made by other space science missions. The telescope will match the incredible image quality offered by Hubble, but with infrared light instead of visible light. We'll go into depth about infrared light in a moment. JWST, Hubble, and many other observatories will work together. They will target some of the same regions of the sky to provide simultaneous or follow-up observations in infrared light. Using infrared imaging at unparalleled sensitivity and resolution to detect the faint infrared light, JWST discoveries will revolutionize and enrich our understanding of the universe. So why study infrared light? The rainbow of light that the human eye can see is just a small portion of the total range of light, known in science as the electromagnetic spectrum. As it was shown, the radio, microwave, infrared, visible, UV, X-rays, and gamma rays. This is what we know as the electromagnetic spectrum. So telescopes can be engineered to detect light outside the visible range to show us otherwise hidden regions of space. JWST detects near-infrared and mid-infrared wavelengths, the light beyond the red end of the visible spectrum. Let's look at this concept with more familiar objects. Visible lights provide us with detailed information about our environment. including colors and textures, as seen with these warm-blooded meerkats and cold-blooded freshwater crocodile. However, in infrared light, we see different details. The meerkats glow dramatically. Their high metabolisms cause them to glow brightly in the infrared through insulating layers of fur. The freshwater crocodile is faintly brighter than the cool ground, which tells us it had been recently lounging in the pool of warm water located here on the lower left corner of the image, which is the warmest thing in the picture. It's been out of the water long enough to start to cool down. Infrared is a type of light our eyes can't see. It's redder than red light. Everything is glowing, even if we can see it with our eyes. Many things like computers, humans, and animals glow in infrared light. Another reason to study this type of light, and more related to astronomy than meerkat, is that in order to capture light that's traveled more than 13 billion years to reach us, from when the universe was only hundreds of millions of years old, we need a telescope that focuses on gathering light that has stretched or redshifted over time into infrared light. JWST sensitivity to infrared light allows us to see the ancient light of the first galaxies, which has been redshifted as it travels towards Earth over billions of years. When the telescope takes its first deep fields, like Hubble's famous deep field image, we will see some of the first galaxies that formed the universe. There is so much more we will learn. So let's explore all of the amazing science it will contribute. And remember these moments, because in 5 or 10 years, what we expected to learn will have profoundly changed for the better. Going back at the electromagnetic spectrum and looking at it in details, the portion of the spectrum of light labeled visible with the colors of the rainbow is what humans detect as visible light. Beyond the red end of the visible spectrum, the wavelengths are longer than the human eye can detect. The portion of the spectrum immediately beyond red is what we call infrared light. Longer wavelengths, including the infrared light, are able to pass through areas of dense gas clouds and other matters in the universe, which we'll see shortly how this changes depending on the wavelength that we're looking at. Shorter wavelengths get trapped, which means telescopes that specialize in visible light can capture some of this light. By detecting longer infrared wavelengths of light with JWST, we will be able to see cool stars and warm planets clearly for the first time. It is worth noting that Spitzer looked at the sky at a longer wavelength or much fainter sources. However, JWST's resolution, which is the capability to distinguish objects that are very close to one another, it's much stronger than Spitzer and also Hubble. That way we can observe not only faint objects, but get a clear image and spectra of them. So by specializing in infrared light, Webb will be able to see what's behind the dust we see everywhere in the universe. For example, the Eagle Nebula's pillars of creation were captured by the Hubble Space Telescope in visible light, on the left here, near infrared light. And the Spitzer telescope in the mid-infrared light captured the same images, but you can see how different they are from one another. Like Spitzer, JWST will be able to see through the dust in regions like this, but at a higher resolution like Hubble. What does each type of light show? In visible light, forming stars are inside dense cocoons of gas and dust, revealing many stars inside and around the pillars. Now, mid-infrared light shows the eroded pillars of gas and dust glowing with the heat from bright young stars. JWST images help us see past dust clouds and figure out what's going on in these dense regions in greater detail for the first time. Now that we know why infrared light is so valuable, let's look at what the telescope will study. Let's start with the early universe. JWST can peer deep into space, capturing some of the first galaxies that formed as the universe cooled down after the Big Bang over 13.5 billion years ago. During this period known as the era of reionization, the universe was a very different place. The gas between galaxies was largely opaque to energetic light, which makes it difficult to observe young galaxies. What allowed the universe to become completely ionized or transparent, eventually leading to the clear conditions detected in much of the universe today? We still don't know that. And when did it begin and how long this process took? With JWST infrared observations, it will help us create the first detailed snapshots of galaxies in the early universe and provide much more information than ever possible before. This new data will allow researchers to analyze individual objects to understand how the surrounding gas changed from neutral to ionized, creating the transparent universe we see today. And how can the telescope capture light from the early universe? As mentioned previously, by looking at light that's been stretched out to longer wavelengths by the expanding universe, which is what we call the cosmological redshift. Light from stars that is emitted as ultraviolet and visible light, it is stretched out to longer wavelengths of infrared light. This is the light the telescope will capture and how it can observe extremely distant galaxies. The galaxy shown in the inset picture was observed as it was 13.4 billion years in the past. That's just 400 million years after the Big Bang. JWST will show us even more galaxies that existed in the early universe. And how will the telescope do this? Researchers will examine individual galaxies in JWST images and data. They will pinpoint how old each one is, leading to the telescope's next science specialty, studying galaxies over time. By viewing the universe at different distances and eras, we have evidence that galaxies change over time. They grow, they collide, and merge with each other. The most distant, earliest galaxies we have seen tend to be smaller and less structured than those in the nearby universe. However, the earliest galaxies in the universe are still undetected. This is because the universe is expanding, and as space itself stretches, so does the wavelength of the light from the first galaxies into further and further infrared light. JWST will examine these early galaxies and eras that follow in new detail, providing essential insight and helping us learn more about how galaxies evolve. What's great about this is that Webb's observations will be added to Hubble's, so we'll learn even more about dust, stars, and galaxies over cosmic time. JWST will also help us learn more about the history of the mergers and growth of galaxies, black holes, and the history of star formation. As I mentioned, the telescope will study black holes, both near us and far from us. In our Milky Way, the telescope will peer through obscuring dust to study the center of the galaxy, specifically at our resident supermassive black hole, Sagittarius A star, and the stars that orbit it. In nearby galaxies, JWST will take high-resolution spectra to learn about the temperatures, speeds, and compositions of the material at their centers. Researchers will use this data to measure the mass of the black holes at the center of the galaxies by mapping speeds of the central gas and stars. The telescope will also study the feedback loop between central black holes, their powerful jets, and the formation of new stars in those galaxies. Quasars are another type of very distant but very bright, active, supermassive black holes. They are among the brightest objects in the distant universe. These supermassive black holes, typically located at the center of their galaxies, are millions to billions of times the mass of the sun. They feed on infalling matter and unleash fantastic torrents of radiation, outshining all the stars in their host galaxy combined. JWST will study the properties of quasars and their galaxies, and how their black holes influence the first stages of galaxy development in the very early universe. So the telescope could help address broader questions of how galaxies form, including the long-standing problem of which came first, the galaxy or the black hole. Next up, for JWST, stars. These pictures here are two views of the same object. It's an area of star formation in the Carina Nebula, nicknamed Mystic Mountain. Visible light shows how scorching radiation and fast winds from super hot new stars are shaping and compressing the pillar, causing new stars to form. But more forming stars remain unseen in its dusty towering peaks over here. Near-infrared light reveals the stars behind the gaseous, dusty veils of the nebula. The foreground pillars become semi-transparent because infrared light from background stars penetrates through much of the dust. A few stars inside the pillar also become visible. JWST view will show us even more details of star forming regions. Its images and data will help us learn about the physical and chemical properties of stellar and planetary systems. It will also give us insight into their formation. JWST can also detect the molecules in star forming regions, including the small Magellanic Cloud shown here. While the telescope will also capture spectacular infrared images of space, its real power is in spectroscopy, which is a scientific method of studying objects and materials based on detailed patterns of colors or wavelengths. Astronomers will use spectra captured by JWST to study mature stars of different sizes, mass, age, color, temperature, evolutionary stage, and formation environment, newly forming stars cocooning dense dark clouds of gas and dust, cold molecular clouds that collapse to form stars, gas and dust ejected from dying stars, and molecules between stars. Also, this is a lot of information, I know, but it's amazing how many things the JWST can do. So another thing it will explore are planets in our own solar system and worlds that are light years away. It can gather data about Mars, Jupiter, which is the one shown above near infrared light, Saturn, Uranus, Neptune, and more distant Kuiper belt objects that's where Pluto is orbiting. And this will help us build a broader picture of the objects in our solar system. JWST will help us better understand Mars's atmosphere, map the cloud structures on Jupiter, Saturn, Uranus, and Neptune, study the seasonal weather and climate on the giant gas planets and their moons, and study the composition of asteroids and Kuiper belt objects. But we know from other missions that there are many more planets out there, outside of the solar system. JWST will also study other planets in our Milky Way galaxy, extending the scientific discoveries of other NASA missions. If you're interested in planets inside and outside our solar system, you should follow JWST news very closely because we're going to learn a lot about this field. Many observatories already study distant planets. What will JWST do differently? Warm planets glow brightly in infrared light, while their host stars usually don't shine as brightly in those wavelengths. Their innate contrast means infrared light is the ideal wavelength range to observe planets around other stars. From its position in space and with its huge mirrors, JWST will be able to capture longer infrared wavelengths of light in high resolution for the first time. JWST's unique abilities to take very sharp and very fast images also allowed it to spot smaller planets than other telescopes. The image shown above is an artistic representation of the TRAPPIST-1 system. Because of their small size, these planets have only been detected, but not studied in greater detail. With its position in space, JWST can add to what we know about systems like this by providing considerably more detail of the planet's atmosphere and its composition. The way JWST will study this about Earth-sized exoplanets is by using a method called transmission. On this graph, we're measuring how much of the light the telescope observes from the star is being blocked by the planet. 100% star brightness means we can see all of the star. When the exoplanet passes in front of the star that is orbiting, it will block the light of the star, but the telescope will be powerful enough to discern between the light of the star being blocked by the solid part of the planet and the light being blocked by the atmosphere of the planet. In other words, this telescope will be able to see the atmosphere of the exoplanets. The yellow arrow here represents the size of the exoplanets that makes that deep on the amount of the light received from the star, while the red dashed lines show how much of that light is being blocked by the atmosphere of the planet. This is an example of how JWST will be able to see those atmospheres. On a more sophisticated level, this is a transmission spectrum of Earth's atmosphere. And before I go too far in the topic, I want to state that JWST will not be able to observe Earth. This is just an example to show how the data, which is in here what we're showing is a spectrum, it's how JWST will produce it when studying distant planets. So when I mentioned that the atmosphere will block the light of the star, I was referring to the molecules in the atmosphere, that they will be absorbing the light of incoming from the host star at specific wavelengths, as shown here. For example, this transmission spectrum shows wavelengths of the sunlight that molecules like oxygen, water, carbon dioxide, and methane absorb. Measuring a planet's atmosphere from hundreds or thousands of light years away is not as daunting as it may sound, though it clearly requires specialized instruments and rigorous techniques like this one. JWST will observe the star's spectrum and then the exoplanets as it passes in front of the star. Scientists will subtract the star's light in the spectrum to see which molecules the planet's atmosphere absorb, which appear as dips in the spectrum as shown here. JWST data will also be transformed into models or maps of exoplanets to provide more information about the exoplanets at each stage of their orbit. By using both imaging and spectroscopy, the telescope will return incredible details about planets we haven't been able to detect with other telescopes. Spectroscopy helps researchers identify the colors, temperatures, motions, and masses of celestial objects, helping us learn a lot more about these distant worlds. Knowing more properties about these exoplanets will also put us closer to answer one of humans' biggest questions. Is there life outside of Earth? So, from the early universe to nearby galaxies and all the way to planets orbiting other stars in the Milky Way, and even our own planets, JWST will give a myriad of new information and probably many more questions than answers. So who's ready for JEP's images, data and discoveries to start rolling in? I know I am. So about 6 months after it launches, JWST will begin its science mission and start conducting routine science operations. And the news releases will start making exciting announcements. So I want to thank you for your attention. And if you have any questions, feel free to ask away right now.
All right. Hector, first, let me say thank you so much for that presentation, just full of such incredible information. I want to remind our audience you can ask questions of our presenter here by just typing them in the comment section there on YouTube, which I see a couple people have already. Hector, before we get started with the audience questions, though, I had a couple for you. We do have some young people in the audience who are pursuing their own education and might be interested in astronomy and astrobiology in their futures. If there's a young person looking at continuing their education and wanting to get their hands on some of this data from JWST in the future, what kind of advice do you have for a burgeoning astronomy or astrobiology student?
So I think I would tell them to, like, the first thing to do is, like, well, the first thing in your mind you have to do is, like, do not give up. Like, if, for example, you are in a university that doesn't offer astronomy or astrobiology, or you are somewhere that is not encouraged, I encourage you to, like, look for other opportunities. I always say to people, apply to any opportunity you see on internet, even if you think you're not gonna get it, because you never know. So, for example, for me, what I did, I wasn't sure I wanted to do astronomy in my undergrad. That was something that I didn't think of until my last year of undergrad. So for me to start looking to create, like, my portfolio of, like, become an astronomer, I had to look for opportunities. And I talked to many professors. I sent so many emails to find an opportunity that would give me to do research in astronomy. And until I landed one, and that was, like, my beginnings, my origin story in astronomy. And from there on, it's, I think I've never stopped applying to things. Well, pandemic changed a little bit my motivation to apply, but before that, I always look to apply to things, and always keep looking for opportunities. NASA has a lot of resources for internships in their facilities. The universities, they have their research experience for undergraduates. If you're an undergraduate, look for that, because there's also astronomy research in different universities, and you get paid. So that's something. If you're worried about your finances and economy, there are most of these opportunities are paid. So I encourage you to apply, never give up, and ask a way. If you need someone that help you, look for someone, and don't be afraid to ask for advice or for opportunities.
Excellent. That's great advice. You mentioned that JWST won't be looking at Earth, but a question that came up for me during the presentation: if there were, say, aliens in another solar system, and they had their own JWST space telescope, and they did look at our planet, what would they see with that telescope that would give away the fact that there's life on Earth? What signature would stand out to them?
So, is my presentation showing still, or
Yeah.
Okay, so let me go back one, two. So, for example, here this was an example that it's showing how Earth would look if JWST was pointing at it, but because JWST won't be able to point at it because it's always going to be facing it outwards, this is just a simulation. However, this could be how the simulation that other JWST in another stellar system would see. And in here, you can see that when they looked at the spectrum, or what we call the fingerprint of the planet, you can see different molecules like water, carbon dioxide, oxygen, and methane. And usually, for example, so it's a complex question though, because let's say we have to think like maybe if that alien life have the same biological system than us. For example, they use oxygen and they exhale carbon dioxide, or those are like the two main sources for to keep the biological life running. Then we might say that, oh, we see, for example, oxygen, carbon dioxide, and methane, which are mostly reproduced by life. And of course, some of this can also be reproduced by other sources that are not life. So this is what we call a false positive. But one of the things to pay attention is that, for example, if we see oxygen and methane, as we see in this picture, usually these two on Earth, there's so many caveats, but on Earth, usually these two, they have like what we call sinks, or things that would take it out from the atmosphere. So if there's something that is not putting oxygen into the atmosphere, in the long run, the Earth's atmosphere will run out of oxygen. So we need other sources, maybe biological or life sources, to put it back. Same with methane. So, for example, here we see oxygen and methane. So that would be clearly like a biosignature, what we call like a signature for life. And you might think, like, oh, we might have found life because we're seeing both of those molecules in their atmosphere.
And that kind of ties into one of our audience questions. Lisa asked, what do you think is the most important biosignature, and how will JWST aid in its detection? And does that, you mentioned if it's life like we find on Earth, are there different kind of biosignatures that would be maybe not oxygen or methane or something else that would stand out?
Yeah, and so for the first question, I would say like, because biosignatures by themselves, just looking, for example, at oxygen, can be a little tricky, and it could give not much information whether there's life or not. I would say biosignatures in pairs, like looking at two at the same time, would be would be more informative whether there's life or not. And I would say, to me, I think it's oxygen and methane that the biosignature pair that is really important, and if life is like on Earth. So those, because we produce methane and we also need oxygen. So there's and also plants, for example, they're the ones who produce oxygen. So if we have those two, maybe there's life. And I think these two, like, seen together, are a big flag saying like, oh, there could be life here. And then, like you said, like, if they're live, their biology doesn't compare to us on Earth. We're the only life that we know of. So if it's different, we don't know what biosignatures we have, and that's something that there's like databases of biosignatures, like possible biosignatures that could cover different ranges of what would be a possible sign of life in other planets.
Interesting. I think this next question from our audience, I think you covered it in the presentation, but Andrew asked, given its unique orbit around the L2 point, will astronauts ever be able to go out and service JWST if something goes wrong, as they had done with Hubble in the past?
So Hubble, I didn't mention this part, and is that Hubble's orbit was an Earth orbit, so it was really close to Earth, and it was something that a space shuttle could get there. However, going to L2, the Lagrangian point, is a little further out, and that one, it's kind of hard to get a shuttle. Like that's something that has been done before, to get a shuttle out of Earth orbit, like into a satellite, and try to bring back the astronauts. They did it for the moon, but not for a, not for a just a telescope. So it might be too far away for servicing. But you know how technology is increasing lately, and we don't know how long JWST could be still ongoing, kind of like Hubble, that it's been more than 20 years. So maybe in the future, but for now, it's a no. For now, there's no plans of servicing JWST.
What is the mission life of the telescope? Do you know?
I should know that. Oh god, I can look it up real quick, because I think I had to read it in my notes. But if someone, I don't know if the public can says it in the chat, but if someone knows, that would be amazing.
We can hope that like Hubble, like Mars rovers, like some other NASA technology, it far outlives its designed expectations, and perhaps in 2075 we will send astronauts out to take a look at JWST or repair it if needed. There was another question from the audience here. Is the telescope solar powered or is it nuclear powered?
I think it does have solar panels, so it's solar powered. The most it has is helium to protect the instruments. So it's mostly solar power, and that's why it has one part of the sun shield. It's always gonna face the sun, and it's always gonna be receiving solar light no matter what. So it's definitely solar powered. And I looked it up, and the mission lifetime is from 5.5 to 10 years. So that would be what they're hoping for.
Excellent. That seems like a pretty conservative estimate, given NASA's track record with how long their technology lasts. Knock on wood. I'll remind our audience, if you have any more questions for our speaker, go ahead and type them in the chat there. Hector, before the program, when you and I were talking, you mentioned that you're one of just many researchers that are going to be looking at data from the JWST once it starts coming in. What is your specific focus going to be? What kind of data are you going to be looking for and doing your research on?
So for now, as you can see in the slide, this is basically what I'm doing right now: simulations of how the spectrum of those planets' atmosphere will look like. How would that fingerprint would look like? And right now, this is what I'm focusing on. For example, I mentioned about the transmission method, which is when the planet passes in front of the star, we can get like a fingerprint of what molecules absorb the light of the sun, of their host star, and from there we can know what molecules are made of. But there's another method called, for example, emission, which is the opposite to it. It's when the planet goes from through the back of the star. Instead of passing in front between the telescope and the star, it would be the other way. The star is like in the middle, and the planet like disappears out of sight because it's smaller, right? And it's just passing through the back. But then from there we can measure how much of that light the planet was. So like it happens in the solar system when, for example, when we see Jupiter in the sky at night, what we're seeing is the reflection of the sun on Jupiter. So we're seeing reflected light of the star. Same thing happens here. If the planet goes through the back of the star, then we're losing some of the reflection, and we can measure that total amount of the reflection that we're losing. And from there, we can get, instead of a transmission spectrum, an emission spectrum. So what were the molecules of the atmosphere? They were emitting the light before the planet went behind the star. And whereas transmission is what molecules are absorbing the light. So it's kind of like the inverse to it. but both of them, combining both of them, could give us more details about the planet's temperature, if it has clouds, or how deep the atmosphere can we see. So right now, that's my project, as to combining these two methods. How much info can we get from the planet? If it's possible, can we assess life on those planets? Which might not be possible with JWST, but there are many telescopes that are planning in the future to have better resolution to look at these planets that are like the Earth.
Is the data the telescope sends back, are you able to determine if you're measuring like a drop in brightness from the star when a planet crosses in front of it? What if there's happens to be two planets in their various orbits that are crossing relatively at the same time? Can you differentiate between the two?
Yeah, so that it makes it more tricky, but like there are methods of like filtering the filtering like what flux is being left, because it's very low probability that two planets would both at the same time go back from on the backside of the star. So, and this tends to happen, like for example, JWST will look at really small stars, and those planets that we're looking at, they have periods or orbital periods. So for example, Earth takes around 1 year to go around the star. So these planets that we're looking with JWST, they will have at most days of instead of years. So it's something that JWST can keep looking for a good period of time, and from there we can then discern like, oh, we see a planet going this amount of times, like the flux is like going deep in at this rate, while this one it's happening at a different rate, and you would see like this kind of like beat, and then you can like from there filter out the different planets that are affecting the flux.
Interesting. Wow, that's fascinating stuff. You mentioned all of the various things that JWST is going to be looking at, exoplanets, black holes, things within our own solar system. It's only one telescope. Who gets to decide where it's looking at any given point in time? It seems like that's a big list of objects for it.
So right now, the first call for proposals happen, and this is when scientists they submit what they want to do with the telescope, how much time they want to use it for, when they want to use it, and from there there's a committee. There's like there's like a like a decision maker board that they select which proposals will be like ideal for to approve and will give the best science. So like it's a process, and people have to apply, and if they get selected, then they can like at a specific time, then they will be able to collect the data. So but then again, like the telescope is going to be like, for example, 24/7 running. So there's a lot of times that it can be intercalated, and there's many times, and the telescope is going to be like 5 years or more. So there's going to be more call for proposals. There was just one, and there's also the proposals from the people that worked on JWST, the ones that were like that created the telescope itself. So they have what they would say priority, because they're the ones who did all the work. So that's how it works. It's a process of approval, like basically everything in academia.
Yep. I can imagine. Did you put in a proposal yourself, or any of your team there at the University of Washington?
I collaborated. I didn't propose one per se, but I was part of teams that proposed one, and I had to produce some data that would help the proposal itself. Unfortunately, the ones that I participated didn't get selected, but others that were related to my work did get selected, and that data won't be public for a while, but then they release it to the public. So once it's public, then we can use it to do our work. So at the end of the day, it doesn't matter that we didn't get it, as long as we have data to use. Then
yeah, because that data is not specific to any one project ultimately, right? Like researchers can use it for a number of different reasons, I'm sure. Well, Hector, I'm not seeing any more questions come in from our audience. I want to say a big thank you to our audience for the questions you had, and for joining us this evening. And Hector, of course, thank you so much to you for putting this presentation together and giving it to us tonight. It's a fascinating topic. I know we're all anxious to see the launch, see it get out to its L2 point safely and unfolded, and start seeing that data come back. So before we conclude our presentation tonight, Hector, is there any final thoughts you'd like to share with our audience?
December 18, 2021, fingers crossed. I think it's gonna be one of the most nerve-wracking days I've ever had in my life. It's been many years waiting for this telescope, and I bet it's gonna be nerve-wracking for many others. But then you gotta think 6 more months till it's fully deployed. So everything has to work perfectly for this telescope. We've been waiting for a long time, and hopefully now that you see the presentation, you appreciate this telescope and we'll be following the news of the upcoming press releases and announcements of discoveries from the JWST.
Yeah, so much great things to look forward to. Well, Hector, thank you so much again. Thank you again to our audience for joining us tonight. And with that, we'll go ahead and conclude tonight's presentation. I hope you all have a wonderful rest of your week and weekend, and we will see you next time at the Museum of Flight. Thank you so much, everyone.